Okay. Welcome. Welcome back to lecture. Shh. Let's get rolling. First thing we have to do is written homework to be turned in. Are you ready? Okay, students with last names A to B. Yep, Christian, I got the B's today. I saw you back there going like this. Let's bring them up here, stack them up here. Thanks. Good. Okay. There you go. Okay, thank you. Right up here. Okay, very nice. Holly Ambrose, very good. Okay. Very good. Okay, man.
Thank you.
Okay, great. Thank you. A through B. All right. That's right. Did you crush it this time? All right. Oh, boy. Okay. A through B. You guys bring your homework down here? All right. Right here. A through B. All right, right here. Thank you. Okay, students with last names C through Z to the aisles. Aisle people, bring them down. Okay, great, thank you. Okay, thank you. Okay. Aisle people. Thank you. Okay, great, thank you. All right, stack it right here. Great. Right in here. Okay, perfect. Thank you. Okay, great. Thank you. Nice. Thank you. Excellent. Wonderful. Okay, great. Thank you. Right in here. Okay. That's it. Thank you. Okay, man. One last stack. Homework. Okay, good. Thank you. Got your homework? Are you A and B? Put it right there. Get your eye clicker ready. Thank you, Lexus. Thank you. Diamante, homework. Let's go. Homework. You got it?
Yeah? Okay, good.
Yeah, pretty
cool.
cool.
You want me to circle it?
No, this is pretty good. This is right. Except I usually use scientific notation. Instead of yeah, times 10 to the 12, 10 to the 12. Instead of E12. No, that's all right. I can't believe it. You did this in ink. Nice.
Well, because I wrote it on my paper. And
Oh, okay. Yeah. All right, good. Homework. Okay, man. Yeah, right here. Okay, man. Thanks. Okay, students. Students. Friends, Romans, and countrymen. I'm ready to start. What about you guys? Get your clickers out. Uh-oh, I see one more homework coming up here. Two more homework. Come on, hurry up. Before the clicker comes clicking. Homework. Okay. That's all right. Better late than never. Good, thank you. Do you have a homework paper? Do you have homework? Angelina, do you have homework? HW, please. Thank you. Very good. Okay, you may now return to your seat. Is it raining out there? See, because I scampered over here to this building at noon because I knew that it was supposed to be raining. It looks like people are getting soaked. Okay. Let me do this later here. Here we go. Clicker session. Rollin. Question number 1 for today. Oh, wait a minute. Hold on. Let me do that as multiple. Okay, this one. Hit the refresh key on your rig. Hit the refresh key, and you'll get. It'll start you with the letter A, and you can select A, B, C, D, E, F, G. Just to see what you guys are voting for. Oh my. No, you got to put in one letter. Don't put in two. Come on, I see somebody with a 2-letter answer. All right, that's better. Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Well, there's a lot of votes here. I'll post the solution on web courses. By the way, I put the talking PDF from yesterday's .camp session. I put it up this morning. I forgot to put it up last night. Other thing I forgot to do was publish your guys' Scantron scores. And if they're in there, I just got to go in and click this little button. And you'll be able to see them. Right now it's muted. We want to keep talking about Chapter 24, Electromagnetic Radiation. We talked about this diagram last time, the dipole antenna, hooked up to an alternating current source. And usually that's going to be a voltage supply. Question? I think everybody knows the answer. Almost everybody voted for the same thing. So there was only a few trip-ups. Because, see, here's the thing. Students bring homework in after I go through the solution, and then they, so. Anyway, so this is, we looked over this diagram. This is one this is image D from one of the diagrams that we looked at. 3/4 of the way through the cycle. And notice that, they didn't do this in the diagram, but I put in blue propagation velocity vectors going rightward. Up here, let's see if I can get my cursor. Up here at the top, right above point P, the field point that they're looking at. And then, those field vectors, the field marches off to the right here. And so this part of the wave is marching off here. Here's the dip in the wave. So this is an upside down field. And they're marching off at the speed of light. So this is like a strobe photo, if you could do that for the electric field. And that propagation velocity is important. It's perpendicular to the electric field, which is represented by these red vectors. It's also perpendicular to the magnetic field. And so, V, E, and B are all mutually perpendicular. Now, here's a picture that we didn't go over last time. This one, this is looking at the same antenna, but now looking at the magnetic field. This is figure 24.2. And a couple things on this. We know that the field line around a wire, a straight wire, is going to be circular. It's going to be in a plane perpendicular to the wire. So this grayish plane looks like a tabletop almost. Think of that as being perpendicular to the wire that's going straight through the roof. So straight from floor to ceiling, and then just like a tabletop is. Tabletop's usually parallel to the floor, and so if the current's going straight up this way, then the field lines are circles in the tabletop, and right-hand rule applies. So if the current is going upward, as it is in this diagram, then the field lines have a circulation that's counterclockwise in this view. So the magnetic field is in the plane of the tabletop, and it's going that way, off to your right. But back over here on this side of the wire, the magnetic field, there's circular magnetic field lines. So the magnetic field over there, it's still on the tabletop, but it's heading over here. So if the wire were going straight up here from the middle of my table, on the front of the table, the magnetic field would be going to your right. But here on this side, the far side of the table, the magnetic field would be going over to the left. And the electric field is still parallel to the dipole antenna. Right? So you got your electric field like this, it's going upwards and downwards, upwards and downwards. And then you got your magnetic field going leftward, rightward, leftward, rightward, and they're all pushing out towards you. Right? So that's the propagation direction. So here's the electric field perpendicular. It's kind of it's hard to draw these things in 3 dimensions. I mean, drawing one vector in perspective is good, but once you get 2 perpendicular vectors like this, it's a little shaky. Anyway, another thing we talked about was the electromagnetic spectrum. And, this, if you type in the word electromagnetic spectrum in Google and then hit images, you'll see like 7,000 different variations of this. I don't like this one very well, although there's parts of it that are nice. This one's it goes from large wavelengths down here, 10 to the 4th meters. These are like your extremely long frequency or extremely low frequency radio waves that the Navy uses. And then down up here, 10 to the minus 16 meters. That's really, really tight. That's gamma rays. By the way, the short wavelength of these X-rays is why they penetrate your skin and get X-ray images. They penetrate your skin and the other soft tissues, but for the most part. But then when they hit the calcium, the apatite molecules in your bones, they stop, and that's why you get the nice images from them. And it's because of the short wavelength. It's also called penetrating radiation because of the smaller wavelength. Ultraviolet. And then I usually refer to this as Roy G. Biv over here. And they've got a different, this is frequencies, I guess. Okay, I usually go, for me, my rule of thumb is 400 nanometers for violet and 700 nanometers wavelength for red, for the deepest red. By the way, I want to go over something with you. This picture, that's a color wheel, right? And you've seen them since like 3rd grade or whatnot, for art class and stuff. And it's good because, actually this one's kind of, now that I look at it, it's not that good. But the idea is that the reds merge into the purples, the violets, and then the violets turn into blue, the blues turn into greens, greens turn into yellows, then oranges, and then back around here to red. And it's a wheel. But light is not a wheel. That's our perception of it. Our perception of red is that the next color after that is either purple or, if you go the other way, orange. All right? But if you go to that's our mental image of it. That's how our brain processes it. But in reality, the electromagnetic spectrum here, there's no red out here. That's ultraviolet. There's no purple over here past the reds. That's the reality. So here's something to think about. Infrared is a red you cannot imagine. It is more red than the reddest red that you've ever seen. Ultraviolet is an even more beautiful violet than the most beautiful violet you can imagine. Now we can't, why are you laughing? It's true. It's there. Our brain is not fitted out for it, but it's there. And it just shows you that, the truth of, if you think about what is happening in our universe, it becomes interesting to think about, as far as I'm concerned. Here are your AM and FM and microwaves. And one thing I usually try to mention, one man's microwave is another man's infrared. So there's no like hard and fast boundary line. You know, one side of that is microwave, the other side is infrared. There, you know, some physicists, it's just like, well, should he measure a distance in centimeters or in meters or in light years? Astronomers are going to think in light years, but a regular scientist might think in terms of meters or nanometers if he's an atomic physicist. So same thing here. And this scale is logarithmic. And you can see that, you know, here's the other interesting thing, and you can jot this down in your notes. The sun puts out most of its light right in here, in the green band. So at the temperature that the sun is, it's about 5,800 Kelvin. The peak output is green. So the sun is, I mean, we see the sun in our atmosphere as kind of a yellowish white circle, glowing yellowish white. But if you were actually on another planet looking at it, you might think, ooh, that's a green star. Okay? But of course, if you're on another planet, then you might still see it as kind of a white star. But the peak color is green, so technically the sun is green. But now here's something interesting. Two things that are interesting. Photosynthesis, right? Plants. Green. It's the chlorophyll, supposedly, that gives it its green color. Now, why is a plant green? Because of the chlorophyll, but it's not absorbing green. That's the thing about it. It's rejecting green. You see a plant, you know, a green plant as green because sunlight is reflecting off the surface and it's not being used. Or more green is being reflected than the other colors. So it's absorbing yellows and reds down here and oranges. It's absorbing blues and violets and indigos. But it's not absorbing as much greens. And yet that's the color that the sun puts out the most of. I have never heard an explanation for that. You know, I mean, if you think in terms of evolution, right? All these things evolve as what do they call that? An adaptation for an evolutionary advantage. What do they call that? Anyways, it's supposed to, you know, your organism's supposed to evolve and retain traits that make survival more easier, right? So why does rejecting the most abundant wavelength of light, why is that an evolutionary advantage? I've never heard an explanation for that. There probably is, but I've never heard of it. Here's another one. It's kind of a cool one. The human eye. You know, a lot of you guys are shooting to be doctors, maybe ophthalmologists. The human eye, the inside of it, is mostly water, right? I mean, it's got other stuff in there, and it's got cells and, you know, the retina and all those cool things. But the inside of the eyeball is mostly water, right? Some wavelengths of light are absorbed by water more readily. You know, water doesn't transmit all frequencies equally. You know which one it transmits the most freely? Green. In the visible band. So your eye is the sun just happens to be the perfect color for an eye made of water. So when you're looking at anything in this world, the one thing that you're getting plenty of is green, because your eye is letting green pass through and get to the retina more than any of the other colors up there. Now, it's pretty good at red too. I mean, it's not like, suddenly it rises for the color green and then it dips down. They're all pretty good, but the peak one is green. So it's kind of an interesting feature of water. Another thing I want to mention to you and reinforce is that astronomers and all scientists make observations all through the spectrum. This is kind of an interesting image, and you can refer to figure 2410. They have a set of four separate wavelength images. They have a fourth image, radio frequency, which this doesn't have. This is a Crab Nebula. It's a supernova remnant. And this is a composite of X-ray images, optical, and infrared. It's a false color image. And you know what's right in the middle of it? You can't really see it. It's right in here somewhere. There's a neutron star that pulses. We can observe that. We can actually see it. We can see the neutron star. That's the leftovers of the supernova detonation. Anyway, so astronomers are always looking at all these things. All right, I want to talk about Maxwell and some of his ideas about waves. There's a paragraph that we're just gonna look at and think about concerning waves, and this is from one of the pages in your textbook. Faraday's law of induction provides part of the basis for the radiation field that we've been talking about. As section 22.4, that's 2 chapters ago, discusses, this law describes the EMF, or potential difference, produced by a changing magnetic field. Okay. So you get some electric field if the magnetic field is changing. And as section 19.4 explains, a potential difference can be related to an electric field. Thus, a changing magnetic field produces an electric field. Okay, good. If the flux is changing, you're going to get some induced current. Now, here's what Maxwell said. Oh boy. There's his picture. Oh my goodness. I forgot to put in, let me pause this. Get my cursor over here. Maxwell, he's kind of, all right, so here's the first 2 quotes, right? Now here's the kicker. This is the one, and this is page 674. Thus the changing magnetic field produces an electric field. Maxwell predicted that the reverse effect also occurs. Namely, that a changing electric field produces a magnetic field. Now that's why we have a wave where the electric field and the magnetic field are both changing and generating the other. It's a mutually inductive form of radiation. And Maxwell's the one that kind of figured out that must be the case. Michael Faraday didn't figure that one out. But James Clerk Maxwell, there's a picture of him. He has the James Harden beard going. And he said, you know what? The way this is set up, we're going to have waves. Now, here's kind of a version of the equations that he was looking at. Go ahead and write down these 2 equations. The first one is delta E over delta X equals minus delta B over delta T. All right, and then the second one is similar. It's got a delta X on the left, but it's delta B over delta X. So the spatial variation is over here on the left. So these are like gradients, rise over run. All right, these 2 guys. Now over on the right, we have minus delta B over delta T. And then On the second equation, we have minus mu naught epsilon naught. And those are the permittivity and the permeability constants. And there's a minus sign in front. And then there's the time rate of change, delta E over delta T. So over here on the right side, we have temporal variation. The top equation, the temporal variation is in the magnetic field. And the spatial variation is in its partner, the electric field. All right. Now down here in the second equation, the temporal variation is in the electric field. Now both of these equations hold. Right? So the spatial variation is in the magnetic field. The temporal variation in the second equation is in the electric field. All right? Now that's what we call a coupled system of equations of variation. Now, one last little side comment here. Remember this product, mu naught times epsilon naught? Yeah, that's 1 over c squared, the speed of light. Now, for those of you that are, many of you are going to become professional users and thinkers of scientific thoughts and scientific information. So from this, we're not going to do much calculation with this, but I do want you to remember that a wave equation, like for electromagnetic radiation, C equals lambda F, very easy, very sweet. But when you see a set of coupled equations like this with spatial and temporal variation and then temporal and spatial variation switching, when you see that tips you off, you've got some waves going. Now this is electromagnetic waves. You can actually do a study of water waves and pressure waves and get similar looking equations for pressure and density and stuff like that. For acoustic waves. Well, much more difficult. Okay, so remember that, whenever you see a potential energy that's a square of some kind of a coordinate, you got oscillation. Whenever you see a quantity that's proportional to the rate of change of that quantity, you have exponential growth or exponential decay. When you have spatial and temporal variations coupled together here, like this, waves. Okay? These two equations can be merged together, and what you'll find is a single wave equation. And that's where C equals lambda F just falls right out. It's pretty sweet. But we're not going to go through that derivation. But do remember, Dr. B, signs of a wave equation. There they are. Spatial and temporal. Now, here's another thing I want to review with you. This is the official speed of light. We know that we have now declared that the speed of light to the nearest single meter per second. Now, a meter per second is about 2.24 miles per hour. Okay? So we know the speed. We've said it. We've decided that that's going to be a constant of nature. Not something to measure, but something to use. Like the international meter is a bar of metal in Paris, France, that's a meter long. I mean, it used to be. That's how it started. I think it's made of palladium or some precious metal like that. The kilogram, the official metric kilogram, it's another chunk of metal, 1,000 grams. Right? And you could look at it. You go to the museum in Paris, and you check it out. All right. And so that's the standard. So this is now our standard, 299.792.458. But I just remember 3 times 10 to the 8. But I mean, if you want to use all your digits, Jade, you can use all these. All 9. If the feeling comes over you. Now, here's another thing about Maxwell. And this is related to electromagnetic waves. He said, and this is back in the late 1800s, the vast interplanetary and interstellar regions will no longer be regarded as waste places, in the universe, which the Creator has not seen fit to fill with the symbols of the manifold order of His kingdom. We shall find them to be already full of this wonderful medium, so full that no human power can remove it from the smallest portion of space, or produce the slightest flaw in its infinite continuity. Now, what is this medium that he was talking about? It's called the luminiferous ether, not matter. But just as waves in the ocean are waves that propagate through the water, and sound waves are pressure waves that propagate through the atmosphere. Out in space, there's no sound. When you watch Star Wars, and they blow up the Death Star, you hear this big explosion and stuff like that. And of course, you can't hear that in space. I mean, you can get greased in space, but you can't hear it. Everything's silent because there's no air out there. There's no pressure waves. So if I was in space and talking, do you ever notice how in Star Wars they have these big hangar decks, and the doors open, right? And these spacecraft, they just come flying in and they just hover and then they land nice and gentle. And then all the soldiers, what do they call those guys? The stormtroopers, yeah. The Imperial stormtroopers, in those white suits with the hats and everything. And they're just marching around there, guarding the planes and stuff out on the hangar deck, and it's open to space. How do they breathe? What is that? It drives me insane. They have stuff that makes noise in space. It just, Darth Vader's, here's the worst part. Darth Vader's, his fighter that he's chasing Luke with, it makes a sound that's different from Luke's fighter. That makes us, they're both making sounds, and you can tell them apart. There's no ether in space. Sound waves need, water, sonar, when we're tracking submarines at sea. That's sound waves, pressure waves in the water. And me blabbing my big mouth up here, that's pressure waves in the air. So they need a medium, and that's kosher. But what we found, and basically Einstein is the one that settled it, that there is no medium for these waves. Right? So that's your lesson here. Maxwell figured out waves in the electromagnetic field, but he thought that they were waving in a medium. And Einstein figured out there can't be any medium. There's no... And here's the reason that they thought that they could measure it. If there's a medium and light is coming to us from the sun, if we're moving one way in the medium towards the sun, light should come to us faster. And if we're moving away from the sun, the speed of light should be less. And, guys measured that, June to December, May to December to November. They measured it and they just couldn't pick up any difference. And so everybody was saying, well, okay, Maxwell thought there was a luminiferous ether. You know what luminiferous means? It means to carry light. The ether that carries light. Luminiferous. Everybody was thinking, because Maxwell, he was the MAN. He was the big shot for electromagnetism and a lot of stuff. And he thought that there was this ether, but nobody could measure it. And so Einstein said, look, guys, you can't measure it because it ain't there. You're coming up zip zap, Because it is zip-zap. There's no luminiferous ether. And that's that's like step one of the theory of relativity, of the two steps. Yeah, Jade.
Why? Like, why does light not need a medium and all the other waves do? Like, what is it about like the nature of that?
Why? Jade, the answer to that is become a physics major, go to grad school, and spend your life join the club. I mean, we all want to know the answer to that. We know that that light does not require a medium. But why that happens to be the case, we just don't. We haven't got. I mean, we try to figure stuff out. We have a lot of stuff figured out, but that's one we. And we're actually going to be talking about that now. We're going to talk about energy in the field. Now, the energy in the field is proportional to the square of B and the square of E. And as I've mentioned before, we ran into that earlier. We ran into versions of that. And I told you and challenged you, and many of you figured out, Anna, that this is reminiscent of harmonic oscillator systems. Anna, I need to talk to you after class, by the way. Okay. So now here's on a volume for volume basis, the energy density, so the amount of joules per cubic meter is symbolized U frequently. It's 1/2 times epsilon naught times E squared plus 1/2 times 1 over mu naught times B squared. And see, mu naught and epsilon naught, they're both in there, Christian. And that means, now they're not together. So the speed of light is, so C, it's not, it's in there, but it's kind of half of it's over on the E and half of it's over on the B, but it's coded in there, all right? And this is how momentum and energy are transported across space-time without a luminiferous ether, without an ether. And so now people still use the word ether. You hear about it. People that are using like radio equipment, radio broadcasters, it's on the ether. So they still talk about it. It's kind of an old-timey phrase. But, momentum and energy are transported across space-time, but not on an ether, just in themselves. Maybe it's tied up to the fact that the Coulomb interaction is 1 over r squared, because that's an infinite range force, or an infinite range interaction, I should say. So maybe that's why, it doesn't require a medium, a physical medium. But, as I said, here's the equation in black and white. It's one of those things. It's one of the pleasures of being a physicist. You get to ponder things that are still mysteries, and real mysteries. Not like some made up thing in Star Wars. Science fiction. This is real stuff. So let's see. Let me ask you a clicker question. Go ahead and hit the refresh button. I'm going to give this verbally to you. I just thought of a good. Now this one, you're not going to see on the screen, so you just have to listen. Question. Which field is the kinetic energy analog? I mean, we're thinking about, look at that. You know, it reminds you of the kinetic energy, or the energy equation for harmonic oscillator. 1/2 kx squared plus 1/2 mv squared. All right, so that's good for harmonic oscillator. Now, type in the letter E or type in the letter B. Which one is the analog of the kinetic energy? And what we would say in field theory, which is the kinetic term? E or B? E stands for electric field, B stands for magnetic. Which of those two? And I'll give everybody a free correct on this one. Let me actually grade it here. But I want to see what you guys... You know, the whole thing about this class is to see what you guys are thinking. No, don't type in the letter A. The only two answers that you can type, I want you to type in are either B or E. So if you typed in the letter A, there's 3 of you. I want you to change that. Okay, 10 seconds to change it. 10, 9, 8, 7, 6. No, not EB. You can't. You have to choose one. Okay, I got to start over again. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, 196. Very nice. Okay, so whoever typed in A, they're not going to get any dinero for this one. All right, let's go to this. The correct answer? Now, everybody's going to get correct, except for this guy up here. I'm not giving him correct. Correct answer, B. Yeah. Who voted for B? Geniuses. And here's how you can think about it. Here's how you can think about it. Shh, 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 shh. Here's how you can think about it. Which force, electric or magnetic, is tied up with the velocity? B. But I'm going to give you both B and E. Correct, so, because that's like a survey. All right, now I want to talk about something called optical rotation and the chirality of organic molecules. Oh, I just heard somebody consternation. Oh God. Organic, orgo. Yeah, molecules are kind of interesting. Now let's, we're pushing through so we can dismiss early today. Polarized light is defined as restricting the electric field to being parallel to a certain axis. It's like going, you have a medium and you have a slot and only electric field parallel to the slot can get through. All right? Now there's all kinds of pictures in the textbook. All right? And in real life, what you do is you have a source of light, and the electric field, the diagrams that we have been using and studying, we've had just one direction, either up or down, for the electric field. But in a real source of light, like an incandescent bulb, the electric field can take any orientation perpendicular to the direction of that the light is traveling. So we could have started with we had electric field up, electric field down, and then we had magnetic field. We have magnetic field left or right and magnetic field left. But we could have had electric field right and left and magnetic field up and down, and it'd still be going out towards you guys. All right, we could have done that. And so that's what this first image says. This is unpolarized light. It's just, any random orientation, and those are the E fields, those red arrows. All right, so a regular chaotic incandescent light source is going to produce light waves that come out with all varying angles of the electric field. So the electric field might not be like this. It might be tilted at 10 degrees or 87 degrees or 104 degrees, relative to straight up. So so that's what this first panel shows you. Now, if you put it through a polarizing material, like for polarizing sunglasses, for instance, we're going to do a demonstration on Monday with this, by the way. Then the only electric field that gets through is the wave for which the electric field is polarized parallel to the transmission axis of the the polarizing material. So this is the polarizer here. And so it basically stops everything else. The only thing that gets through is the stuff that's upright like this. Up and down, up and down. There's no sideways E's. There's no 37-degree E's. There's no 82-degree E's. There's just up and down E's. And those are the only ones good. Now, the intensity on the other side of the polarizer is going to be a little bit less because you're cutting out a lot of your light. Okay? But, that's how light's polarized. Okay, now, the magnetic field B is also polarized 90 degrees. It's not pictured on this diagram. But, whatever the E is, the B field, the magnetic field, is going to be 90 degrees away from that. All right? It's not in this diagram. But, if you have only up and down E's, you have only right, left B's. If the propagation is out towards you guys. All right? Okay, so that's what polarized light is. Now, here's the cool thing about it. Louis Pasteur, the great scientist from France, who is a very interesting guy. If you ever feel like reading a biography of a famous scientist, he's definitely a good one. Michael Faraday and Louis Pasteur, the middle of the 1800s and late 1800s for Louis Pasteur. Did you know that Louis Pasteur, his PhD was in physics? He studied, of course, the greatest scientists, just like Sir Isaac Newton. Yeah, Louis Pasteur, he started out in physics. And, crystallography was what he studied. And he made, but he was one of these guys that will be able to, you pose him any kind of a problem from the barnyard to the back of the side of the moon. He'll tackle it and he'll grapple with it. Now, in his day, and still to this day, in France, they're famous for making wine. All right? And one of the problems that they had was that wine would go bad. You'd store it in bottles, store it in kegs and whatnot, and if you didn't use it, before too long it would go bad, and sometimes it would go bad immediately. So they were looking at all the different kinds of organisms, and back in Pasteur's day, people didn't know about proteins and stuff, amino acids and whatnot, but they did know about tartaric acid, So he made a study of tartaric acid and solutions of the tartaric acid that was refined or extracted from the wine leftovers. And he said, well, let's look at this stuff. And so he made a solution with it, and what he found was that he sent polarized light through his solution. And it went into his sample, his solution of tartaric acid, dissolved into probably water. Tartaric acid from, some winery outside Paris probably. And that was a sample. And he passed his beam of polarized light and then found that it came out polarized, but its polarization axis was rotated. Now, that's not happening over here. This diagram is just polarization. What Pasteur said was he sent this in vertical polarization, so up and down electric fields. He sent that into his solution, and then he found, dude, on the other side, it was tilted a few degrees over. So he had to adjust his polarizer, what they call the analyzer, on the other side. And he found that he didn't get full transmission unless he tilted at a few degrees, and that the wider the container, the more distance he had to go through the container, the more it tilted. And that's called optical rotation. All right? And I'm going to try to get a demonstration. You know what you could do, probably? I know you guys do a lot of exploring around on the internet. You try to decipher my lectures and whatnot. Type in optical rotation and see what YouTube's got. I should have done that before a lecture. But optical rotation, here's the cool part about it. It's cool. You can get some compounds in solution that'll rotate to the left. And so some of your stuff will tilt your polarization axis a few degrees this way. And some will tilt your polarization a few degrees this way, to the right. So you can classify different compounds by whether they optically rotate to the left or to the right. And guess what? And that's what we call the chirality for that molecule. And here's the cool part. Now, for you guys that are in life sciences, this is a profound mystery. Pasteur found that he could get optical rotation from tartaric acid solutions if the tartaric acid came from wine, from a winery. But if he synthesized it, in the lab, synthetic tartar, he wouldn't get any optical rotation. And that's because biological systems only produce certain molecules that are left-handed. And other molecules, biological systems like a grapevine, only produce other substances that are right-handed. So when he was synthesizing in the lab his tartaric acid, he was coming out with right-handed and left-handed tartaric acid molecules. So he didn't see anything. He didn't see any rotation. But when he used the stuff that came out of the biological origin of the winery, the grapevine, the fruit of the earth, he got rotation. And so this is the strange mystery that that we don't know why it is. Amino acids of biological origin, left-handed. Sugars of biological origin, right-handed. Across the cosmos, we think, we don't know why it is. But maybe one of you guys, you get through med school, you're doing biomedical research, you'll find out why. And my wonderful students, I would like to know the answer to that too. There's stuff in this world that is still ready for you to discover. Okay, Jade? Lots of stuff to discover. Lots of cool stuff. Like why do, we can synthesize amino acids. We can, you know what? When you go to the GNC or to the what do you call those places? Health food store, and you buy amino acids like lysine. This one over here on the left, that's lysine. You buy L-lysine. You don't buy R. They make it, but your body wants L-lysine. It doesn't want R-lysine. Same thing with sugars. All right. Wiley Plus homework, I'll have it ready for you by noon tomorrow, hopefully sooner. And we are now done with chapter 24. You are dismissed. A little bit early today.